Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for generate parenthesis problem. Let's look at the problem description. We are given n pairs of parentheses and we have to generate all combinations of well-formed parentheses. Let's take a look at the example 1. So in this case, we are given 3 pairs of parentheses, out of which we can generate 5 combinations which are well-formed. Well-formed means for every closing parenthesis there must be a opening parenthesis present in that string. So if you see here, so first 3 are open parenthesis, and then we have for each open parenthesis we have seen there is a close parenthesis present. And in the second case, first 2 are open and then closed, then one more open and close parenthesis and then close parenthesis. So the first and last is a pair, and the second and third and fourth and fifth. So in the case of single pair, we get only one string. The constraints are, so the number of pairs is ranging from 1 to 8. Let's look at the approach to solve this problem. So for this input, the number of parentheses pair is 2. So that means totally we can have 4 parentheses. Using this 4 parentheses, we can generate 2 to the power 4, 16 possible combinations of these parentheses. This is some of them. This one is invalid because this close parenthesis is not followed by any open parenthesis pair. So this is not valid. And also this is also not valid because this parenthesis has a pair, closing parenthesis, and then immediately we see another closing parenthesis which doesn't have open parenthesis pair. So this is also not valid. And this one starts with the open parenthesis, so this is also not valid, and this is also not valid. But this one, this has open parenthesis and open parenthesis followed by close parenthesis. This two is pair, inner pair, and this is the outer pair, so this is a valid parenthesis. This one starts with open parenthesis and then it has the close parenthesis pair, and then open and close parenthesis pair, so this is also valid. So these two are valid, so the expected output is this. So these kind of combinatorial problems can be solved using recursion easily. So as I said earlier, with n number of pairs we can generate 2 to the power 2n number of combinations, and then we can pick up the valid combinations and return. Okay, so that is the exhaustive search. But if we keep track of the number of available or used open parenthesis and close parenthesis count, then we can avoid generating all possible combinations. Instead, we can generate only the valid combinations while we doing the recursion. Okay, for example, for this input, initially the left number of left parenthesis is 2 and the right parenthesis is 2. Okay, and at each level we make a recursive call. We make two recursive call, one which includes the open parenthesis and the other recursive call which includes the close parenthesis. Okay, as we make a call and include the particular parenthesis, we have to decrement the corresponding count. For example, in this case we include the open parenthesis, so we decrement the open parenthesis count, and here we include additional open parenthesis, the count becomes 0. Then if we try to include one more time the open parenthesis. We run out of open parenthesis, so we ended up getting -1. So this is invalid combination. Okay, so we can ignore this path. And from here we can include the close parenthesis and decrement the count, and include one more time close parenthesis, we decrement the count. Finally we get both parenthesis count is 0. In this case we have a valid parenthesis. This is a well formed parenthesis. So open parenthesis, and then followed by the close parenthesis, close parenthesis. This is a valid string. So we include that to the output list. Same way here we include open parenthesis, we include close parenthesis, we include open parenthesis, we include close parenthesis. So in this case finally we ended up both counts are 0 in this node. So this is a well formed parenthesis. Okay, and one more case is if we try to include the right parenthesis first, then we ended up having the left count is higher than the right count. Okay, so if there are no open parenthesis included prior to this, that is an invalid combination, as we see here. So we always starts with the open parenthesis and then we expect the corresponding close parenthesis, but in this case without any open parenthesis we see the close parenthesis. So in that condition we see the left count is greater than the right count. So whenever we see this condition we can backtrack. We do not have to proceed further to generate the string with the length 4. Okay, so there are 3 conditions in which we backtrack: when the left count becomes less than 0, or the right count becomes less than 0, or the left count is greater than the right count. In these 3 cases we backtrack. So that's what I am indicating in the purple. And whenever we see a left and right count as 0, that means we are seeing a well formed parenthesis. We can include that string in the out list. So basically we can solve this combinatorial problem using a recursion with backtracking. Okay, so that's what I listed here. With n pair of parentheses we can generate 2 to the power 2 times n parenthesis combinations. In that combinations we can check and return the well formed parenthesis. This is an exhaustive search. To reduce the number of processing we can use the backtracking by keep track of the open and close parenthesis count. And whenever we include the left parenthesis we decrement that left parenthesis count and include the left parenthesis in the byte array. And then whenever we include the right count we decrement the right count. Whenever we include the right close parenthesis we decrement the right count and include that close parenthesis in the byte array. And we convert that byte array into a string whenever we see both left and the right count is 0. Let's look at the flowchart. Input for this procedure is the left count and the right count and the parenthesis slice and the address of the output list. Okay. First we check the backtracking condition. If the left count is less than 0, or the right count is less than 0, or the right count is less than the left count. If any one of these condition is true, that means the combination is not well formed, so we return. Otherwise, we check the base case where both left count is 0 and the right count is 0. In that case, we are seeing a valid well formed parenthesis combination. So we convert that parenthesis slice into a string and add that string to the output list. Okay. If both are not equal to 0, then what we do is we make two recursive call. One recursive call include the open parenthesis into the parenthesis slice and decrement that left count and call the helper function. And the second recursive call include the close parenthesis into the parenthesis slice and decrement the right count and make the recursive call. So this recursion continues until both the counts are 0 or the backtracking condition is met. Finally, the out list will contain the well formed parenthesis list. Let's move on to coding. First, I initialize the parenthesis slice, which is a slice of bytes. Then I initialize the output list, which is a slice of string. Then I make a call to the helper function that takes the left and right count and the parenthesis slice and out list, address of the out list. And then I return the out list. Next, I am going to implement the helper function. Which takes the left count, that is for accounting the open parenthesis, and the right count accounting the close parenthesis and the parenthesis slice and the output list address. First, I check the backtracking case. Whenever we see the left count or the right count is less than 0 or the right count is greater than right count is less than the left count, then we can return, because this will not create a well formed parenthesis. Now I am checking the base case where both the left count and right count is 0. In that case, the parenthesis slice has a well formed parenthesis. So in that case, I convert the parenthesis slice into a string and add it to the output list and return. Then I make a recursive call for the case where we use the open parenthesis. Let me fix the function name. So in the case of including the open parenthesis, I decrement the left count and then add the open parenthesis to the parenthesis slice. Then I make a recursive call to use the close parenthesis. In this case, I decrement the write count and include the close parenthesis in the parenthesis slice. Next, I'm going to run the test cases. All the tests passed. Next, I'm going to submit this program. Cool. This program is accepted. Next, I'm going to do the code walkthrough with sample input. In the generate parenthesis function, first I initialize the parenthesis slice with empty slice of byte, and the output list is initialized with empty slice of string. Okay. Then I make a call to generate a parenthesis helper function with the left count is n and the right count is n. In this case, the n is 2. So that's what we are seeing. The left count is 2 and the right count is 2, and the parenthesis is slice is empty and the output list is empty. Inside that helper function, first we check the backtracking condition. If the left count is 0 or the right count is 0 or right is less than left count. So in this case, none of them is true, so we are proceeding, and then we check the base case. Left is 0 and right is 0. In this case it is not, so we are proceeding further. Then we make a recursive call to include the open parenthesis. So we are including the open parenthesis, so that is added to the parenthesis slice. Okay, and then we decrement the left count, so that's left minus 1. So that's what we are seeing. In the frame 2, the left count is 1 and the right is 2. And again, when we enter, none of the condition is true. Backtracking condition is also false and the base case is also false. So next we are again making the recursive call by decrementing the left count. So now the left is 0 and the right is 2. So the parenthesis slice have 2 open parentheses. Okay. Then we check the backtracking condition and the base case, both are false. So we are again trying to include another open parenthesis, but we already used both open parentheses available to us. So now the left count becomes minus 1. So we call the helper function with minus 1 as the left count and the 2 as the right count. So the moment when we enter here, we check the backtracking conditions. In this case, this is true. So we are not proceeding further because this will lead to us to an invalid combination. Okay. So in that case, from here we make another recursive call to include the right parenthesis. Okay. So that's why we decrement the right, and then there we check the backtracking condition and the base case, both are false. So this case we can already see that -1 condition for the left count, so we do not have to look at it. So again we make a recursive call to include the another close parenthesis. So in that case we see both the left and the right count as 0. That means what we are seeing is the valid well formed parenthesis. So open, open, close, close. So the inner pair, outer pair. So the moment we see this, the base case condition is true. What we are doing is we are converting that parenthesis slice into a string and then add it to the output list. So we are seeing that in the out list. We come back to the frame 2 and here we include the right parenthesis. We come to the frame 2 and we include a close parenthesis. So we decrement the right count and we are seeing that close parenthesis added to the parenthesis slice. Then we include the open parenthesis. So we decrement the left count and then we include the right parenthesis. We decrement the right count. So the parenthesis slice have a well formed parenthesis. So we convert that into a string and add it to the output list. But in this case, if we go this route, the left, when we decrement, it becomes -1. So the backtracking condition is true. So we will not proceed further and we return back. Same way in the root, if we try to include the close parenthesis when there are no open parenthesis included, in that case we see a condition where the left count is 2, right is 1. So the left count is greater than the right count. So that makes the backtracking condition true. So we return back. So there is no point in proceeding further. All combinations generated from here onwards will be invalid. So there is no point in proceeding further. So we are backtracking. So because of using the backtracking, we cut down the processing time into half. Otherwise, the same number of processing done here will also be done on this under this node. So by using backtracking, we are optimizing this algorithm. Next, I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. So the number of parenthesis pair is 2. Okay. So for that, the total number of parentheses available is 2 times 2, 4. So we need to generate a string which has 4 parentheses in it and also well formed parentheses. So in the call stack, only at the level 4 we can see the byte slice have 4 parentheses in it. Okay. So the total number of nodes in a tree with level 4 is 2 to the power 5 minus 1, 31 nodes. Okay. In order to generate a 16 possible combination, we have to make these many recursive calls, 31 recursive calls. Okay. But if we use backtracking condition in our recursive procedure, we can reduce that by half. Okay. So as we see in the previous code walkthrough section, we can see the right tree is completely ignored because of the backtracking check. So the total number of recursive call needs to be made is 2 to the power n. So that many times, 2 to the power n times, we have to do these processing, checking the backtracking condition in the base case and then adding that parenthesis to the slice. These operations are done 2 to the power n times. So the time complexity is order of 2 to the power n. And with respect to the space complexities, we use stack space. because we are making recursive call. And also the call stack's length is 4. So 2 times n. N is the number of pairs. And then the parenthesis slice, in which we include the open and close parenthesis as we call the helper function. So that slice maximum size is 2 times n, because we need to generate a string with this length. So the total space we need is the stack space 2 times n plus the parenthesis slice size 2 times n. So 4 times n. So we are removing the constant factor out of this, and the space complexity is order of n. So we are ignoring the space required for storing the output in the space complexity analysis. So that's why I did not include the space required for this string array. Thanks for watching this video. Have a great day.